Finishing this from 5-3 yesterday. It's actually working out kind of nicely, talking about these general shapes from 5-3 leading into 5-4, which we'll get through today as well because that's actually graphing and analyzing the graphs. But I need it quiet, please. Before we get to the examples, there's a lot of information that's on here. It's all related. But not only do you need to understand how to graph polynomial functions, which we're doing as part of 5-4, 5-3 is setting you up so you understand what your graphs should look like. And so there's a lot of things I'm going to be kind of reading through, pointing out, just saying in general, you have to understand the characteristics of these graphs. Otherwise, they're not going to make sense. So on this sheet, it gives 6 different graphs. These are the general shapes of up through degree 5 polynomial functions. And in these graphs, it shows the maximum number of times that the graph of each function may intersect the x-axis. So again, I'm pointing out the word there, the maximum number of times. It is not the number of times it has to cross the x-axis, but the number of times it could cross, the most number of times. And the number of times a polynomial could cross the x-axis, excuse me, is the same as the degree of the polynomial. So I just am going to do a quick refresher with you on the board with quadratics. I'm going to draw kind of 3 parabolas on the same graph. So we saw that a parabola could cross the x-axis twice. It could only intersect the x-axis, in which case that would be once, or it wouldn't have to intersect at all. So a quadratic function, we talked about how that is a polynomial. The degree is 2. So the maximum number of times it could cross is 2, but it doesn't have to cross that many times. So with these listed here, it gives a constant function. The degree is 0, and notice on this graph it doesn't cross the x-axis. Now, if the constant function was actually on the x-axis, it would cross it infinitely many times, but that's a special case. In general, a constant function will not cross the x-axis. Linear function of degree 1 at most will cross once. Quadratic function of degree 2 at most crosses twice, and so on. Cubic function of degree 3 at most 3 times. Degree 4, and it does give that special name, quartic function, or you can just say polynomial of degree 4, at most crosses 4 times. Degree 5, at most 5 times. Okay, another thing before I talk about now the domain and the end behavior that's listed below, there's not a general shape. For example, like all quadratic functions are parabolas. All polynomials, it depends on the degree, what shape it's going to have. So we know all linear functions are lines, all quadratic functions are parabolas. When you get into higher degrees, here's how you can have an understanding of what the graph should look like, or if you're given a graph, how you can estimate or guess what the degree is. The degree is the number of directions that the graph will have. What I mean by that, I'm going to go back to quadratics. There's a degree of 2. There's 2 directions. The graph is either going to go up and then down, or it could go down and then up, but there's 2 directions, up and then down. So a cubic function, degree 3, if you take a look at this graph, all cubic functions will have this general shape. And notice there's 3 directions. This one goes up and then down and then up. Up, down, up. It could start the other way. It could go down and then up and then down, but it'll have 3 directions. So the degree 4, notice there's 4 directions, down, up, up. Degree 5, there's 5 directions, up, down, down, up. So that can at least help. I know I'm kind of looking ahead. We're not there yet, but when you're graphing these, we are doing that today. It's just on 5-4's note sheet. That's how you can have, you know, an estimation as to if you're graphing it correctly. Are the directions matching the degree? So then the last part on this page is leading us into end behavior. So all polynomial functions have a domain of all real numbers. So for every polynomial, the domain is all real numbers. The range will vary based on the function itself. And then we are going to be talking about the end behavior. So the end behavior, just kind of like it's described in the name, is talking about the ends of the graph. So where you would draw the arrows, those are the ends you're looking at. And you'll see when we go through examples how I'm going to ask you to write this, but it's the behavior of the graph of f of x as x approaches positive infinity, which is written in this notation. So if you see x arrow positive infinity, that is read as x approaches positive infinity, and then or as x approaches negative infinity. And like I said, we're going to talk about this more in depth as we actually go through it. But the degree and the leading coefficient of a polynomial function determine the end behavior of the graph and then also the range. So that's bringing us onto the key concept box on the next page. Now, this is good information. I'm not reading through this entire box with you. I'm going to point out some key things that when you're looking at this as a reference, what you should draw your attention to. It's not by any means anything you need to memorize what's in this table. I want you to understand it, not memorize it. So what you should notice is the first column. These are showing even degree polynomials. So it gives a general parabola. But all even degrees, so degree of 2, degree of 4, degree of 6, and so on, they will all have the same end behavior. And then they're giving 2 graphs for an odd degree. So all odd degree polynomials, degree of 3, 5, 7, 9, so on, they will all have the same end behavior. So the graphs won't look the exact same, but they will have the same end behavior. And then the only difference why they're giving 2 for each is it's also showing if the leading coefficient is positive versus negative. In general, when you're listing or when you're saying end behavior, you will have a graph to look at. But if you can start to form a relationship between the degree and the leading coefficient and the end behavior, any future math you're taking, that'll kind of set you up when you get to talk about end behavior more in those classes. But here, like I said, you're going to have a graph to look at, so I'm not going to focus too much on how the leading coefficient plays in. That it really plays into the direction the graph is headed. But then it does give the end behavior for all 4 of these. So, like I said, your end behavior is going to look like one of these 4, but you do not have to memorize this. I'm going to explain at least one of these. You just have to understand how to write it. We're also going to go through 2 examples of it. So I'm actually going to look at this one. So I guess the second box, the top right, is the one I'm going to pick to look at. So first of all, what I want you to notice with all of these, if you have an even degree, the end behavior again is you're looking at the arrows. For an even degree, the end behavior is the same. Both ends will go in the same direction. So if I gave you a graph and I said, tell me if this is an even or an odd degree without giving you the actual function, if the end behavior, if both ends are going up or both ends are going down, it's an even degree. Odd degrees will have opposite end behavior. One end will be going up, one end will be going down. Okay? So if we look at this one, I know they have the end behavior written there for you, but I want to explain how they got this, so I'm going to write it out again. So end behavior is always going to look this way. How I usually set it up is I say as x approaches, so with an arrow negative infinity, and then I also have as x approaches positive infinity, and then I list after them what f of x is doing. So when x is approaching negative infinity, if you think of your x-axis, when you're approaching negative infinity, so your x values are getting larger but in the negative direction, you are looking at the left part of your graph, which for this graph given would be this part here. So you're looking at the left part of your graph, and then you're saying, okay, when x approaches negative infinity, what is f of x doing? What are the y values doing? And in this case, the y values are going down. So f of x would also be approaching negative infinity because those y values are going down. And then when you say as x approaches positive infinity, so you, again, think of your x-axis when the x values are getting larger and larger in the positive direction, you're looking at the right part of your graph, so that would be this end here, up here. And as x approaches positive infinity, that end is going up, so f of x is also approaching positive infinity. So we're going to go through two other examples where it's, I know I even wrote it a little bit differently. They kind of wrote the reverse. They said f of x as x. But this, when I say describe the end behavior, I'm looking for this type of explanation. So not in words, both ends go up, both ends go down, but I want to see this. So I'll kind of guide you through that when we go through the examples, when you have your review and things like that with the quiz. But if you also know even functions have the same end behavior, odd functions have opposite, that is helpful to know. And then another thing with the zeros of a function, before we actually get into the examples, and you'll see how this all ties together. The number of real zeros a polynomial function has can be determined by examining the graph. The real zeros occur at the x-intercept. We've talked about that idea before. So the number of times a graph crosses the x-axis equals the number of real zeros a function has. So in general, this is another way to determine if a function has an even or an odd degree. Other than looking at the end behavior, you can look at the zeros. An odd degree function will always have an odd number of real zeros. Okay, so if I gave you a graph and there was one real zero, one is an odd number, you know the function is an odd degree. Even degree functions will always have an even number of real zeros or none at all. Now the end behavior is why an even degree can get away with having none. So it gives two example graphs to describe this. Notice for the two that are even, end behaviors of both are the same. The first one has the same end behavior going down, and the graph is completely below the x-axis, so it never crosses. So it's still an even degree, but doesn't have any x-intercepts or zeros. The second one, notice there's 4. So it's an even degree, has an even number of zeros. And then for the two graphs for odd degrees, notice their end behavior is opposite. The first one has 3 zeros, the second one only has 1, but they're both an odd number of zeros. So an odd degree function has to have at least 1 zero, and it has to have an odd number of zeros. I do want to draw your attention back up here. So a quadratic is an even degree and has to have an even number of zeros. This graph, you can clearly see there's 2. This graph, you can say there's 0, which is fine. This graph only has 1, but 1's an odd number. This is called, and I mean, if you wanted to draw this on your sheet and write it, you can, you don't have to. But this is called a double root. I'm just going over this because I had it drawn on the board. A double root is when a curve, like if it approaches the x-axis and it just touches and then comes back down. So for a parabola, if the vertex is on the x-axis, that's a double root. So when that happens, it still counts as 2 zeros. Even though it's technically one number, it still counts as 2. So if you see that on a graph, that's just kind of a side note that might be helpful to know though. Okay, so now actually getting into examples. And these are just, I'm going to highlight over these graphs so you can see them easier if you look at the screen. But these are just describing end behavior, determining if the function's even or odd degree, and finding the number of zeros that it has. So that's the direction state above. I'm going to kind of list this as 3 separate questions for each. So question 1 says for each graph to describe the end behavior. So let's label that as 1. So here's how I set up end behavior. I'm going to describe it the same way I did when I went through that key concept box. So it's always going to start as x approaches negative infinity, and then as x approaches positive infinity. And after each one, you're listing what does f of x approach. So when x approaches negative infinity, that is the left part of your graph. And when x approaches positive infinity, that is the right part of your graph. Okay, so we're looking at the two ends. So when x approaches negative infinity, the left part of the graph, what would you say f of x is approaching? Positive infinity or negative infinity? Positive infinity. It's going up. So the left part of the graph is going up. Okay, and then as x approaches positive infinity, so that's the right part of the graph, what does f of x approach? Negative infinity, it's going down. Okay, so I'm going to highlight the only 2 things that will ever change from example to example. These are the only 2 things that would be different from example A to example B. Everything else, the setup would be the exact same. X always has to approach both positive and negative because those are the 2 sides of your graph, and then you say what the 2 ends of your graph are doing. Are they going up or are they going down? So positive or negative infinity. Questions on the end behavior there? Okay, so I'm actually going to combine these 2 examples. Let's just go through, we'll come back, we'll kind of go through end behavior for both at the same time. So end behavior for B, so I'm going to set it up the same way. As x approaches negative infinity and as x approaches positive infinity. So we have our 2 ends, and both ends are the same. F of x is approaching negative infinity for both. It's going down for both. So as x approaches negative infinity, f of x is also approaching negative infinity. As x approaches positive infinity, f of x is approaching negative infinity. So both ends are going down in that case. Okay? Questions on those? All right, then for the second question, it says determine whether it represents an odd or even degree. What would you say for A? Is A odd or even? Odd. What about for B? Even? It doesn't ask you to explain why, And actually, I mean, you could write it for both. Just for A, there's two different reasons you could give as an explanation for why. So Sierra, you right away said it was odd. How do you know? Okay, so it's an odd degree because the end behavior is opposite, or opposite end behavior. So if you wanted to write reasons for B as well, you could say it's even because it has the same end behavior. What's another reason you could say as to why this is an odd degree? What's another piece of the graph that tells you it's odd? What? An odd degree will have an odd number of zeros. This has an odd number of zeros. So I'll say odd number of real zeros. So for the even degree, there's 2 real zeros. So that could be used as a reason as well. So just 2 things on a graph that tell you, it doesn't necessarily tell you what the degree is, but tells you if it's even or odd. Okay? And then question 3 is stating the number of real zeros, and I kind of already have that circled on each graph. Graph A, there are 3 real zeros, 3 x-intercepts. And for graph B, there are 2. Okay, so because we're now going to move on to the 5-4, but this is going to tie in nicely because what we talked about here can help you make sure that you're graphing a polynomial correctly. If you understand what the end behavior should be based on the degree, how many zeros it could possibly have, that's all helpful when you're graphing and analyzing your graph, making sure it's correct. Before I move this, questions on this? Okay. So then for (5-4), as I said, this just ties right in because now you are graphing a polynomial function yourself. When we graph, we're also going to be talking more about the zeros, not how many it has, but actually locating them. We did that already with quadratic. So you're going to notice this is something you've done before. But then we are going to talk about something new, and that's the relative maxima and extrema of a graph. So we'll talk about what that is. But how you graph a polynomial function is by making a table of values to find several points. How many points you have to have depends on your function. So I'm not telling you how many points. I will tell you as we go through example 1 how to know when your table is good enough. But there's not a set number of points you should have. It depends. You then connect them to make a smooth continuous curve. Make sure when you draw it in it's not pointy. It's not jagged. It should be smooth. Think of how you drew a parabola. It wasn't a V, but it was rounded. It says here, knowing the end behavior can assist you. We'll talk about that. So in example 1, we are graphing f of x equals negative x cubed minus 4x squared plus 5 by making a table of values. You may want a calculator to help you make your table. All right. Here's how I go about making a table for these. Because just by looking at this function, I have no idea how many points I'm going to need. You can plug in whatever x values you want. I typically start by plugging in 0, and I'm going to put that somewhere towards the middle of the table because I'm also going to have to plug in positive and negative numbers. but I always plug in 0 first. Okay, so if I were to plug 0 in for x, what would the y value be? 5. Okay, so now pick a direction to go, whether you want to plug in positive numbers next or negative, and you keep plugging in numbers in that direction until you get a y value that doesn't fit on your graph. So I'm going to go in the positive direction first. I'm going to plug in 1. And I'm going to also show you, some of you might already know this, if you have a calculator like mine or similar to mine, your calculator might be able to do this. Like I said, you might already know that your calculator can do this. If you don't, well, some calculators can't do this. It depends on the model. So as we go through this, I would make sure on your calculator, whatever calculator you're using, that you can get the correct values. Because if you can't, then when you're working on your example today later, let me know and I can see how you're typing it in, what's going wrong. So when I type this in, I would type it in like wherever I see an X, I would put the number I'm plugging in parentheses. So for example, I have negative, and then in parentheses, I'm going to put 1, close the parentheses, raised to the third power, and then minus 4, parentheses, 1, close the parentheses, squared, plus 5. So when x is 1, the y value is 0. And then, again, I keep going in that direction, so I'm going to plug in 2 next. Make sure you do go in order. But now, rather than retyping this in, I can just hit the up arrow and arrow over it. Wherever I typed in 1, I just type over it and put 2. And then I don't have to keep typing in the same thing over and over and over again. So when I plug in 2, I get negative 19. And this is what I mean. I just got a y value that does not fit on my graph. So I'm still writing it in the table, but that means I want to now change directions. I don't want to plug in 3, because that's going to be an even lower number. I'm going to instead start plugging in negative. So I'm going to plug in negative 1. So because I have to add the negative in there, I'll retype this for this one. So I have the negative sign for negative x cubed, negative parentheses, negative 1, parentheses to the third power, minus 4, parentheses, negative 1, parentheses, squared, plus 5, enter. So when x is negative 1, the y value is 2. So then I'm going to plug in negative 2, so I can arrow up and just change my 1s to 2s. So when x is negative 2, y is negative 3. So then I need to keep going, plug in negative 3. When x is negative 3, y is negative 4. That still fits, so I keep going, plug in negative 4. So this is where I'm saying you don't know until you're actually doing this how many points you have to plug in. When I plug in negative 4, the y value is 5. Plug in negative 5. And the y value is 30. Okay, so I'm off the graph, so I can stop. So this particular graph took 8 points. You just don't know exactly how many you'll need. So now, before I start graphing this, here's something to consider to make sure your graph is going to be correct. What is the degree of the function? 3. Okay, it's an odd degree. So when I graph this, should I have the same end behavior or opposite end behavior? Opposite. It's an odd degree. I should have opposite end behavior. I'm just going to put opposite ends. In terms of zeros, the most I should have is 3, but I should for sure have an odd number of zeros or x-intercepts. And the most I should have is 3. So I'll put at most 3. So do you have to write this stuff down when you actually graph on your quiz? No, but understanding the graph just helps you make sure that you graphed it correctly. So when I'm done, if my end behavior, if both ends are pointing up, something's wrong. If I have 4 zeros, something is wrong. So that's where I'm saying understanding the graph can be helpful. So when I actually graph this, I know negative 530 obviously doesn't fit. So when I go to negative 5 for x, I'm just going to put a point above my graph to know that my graph starts up there. Okay, and I'm not starting down here. And then I'm going to plot the rest of my points. So negative 4, 5, negative 3, negative 4, negative 2, negative 3, negative 1, 2, 0, 5, 1, 0, and 2, negative 19 doesn't fit, so I'm just going to put a point below the graph to know that it ends down there. So I do know I'm starting at the top, ending at the bottom, so my end behavior will be the opposite. Okay, so I know that kind of checks off. I just then, when I'm done, have to check that I have an odd number of zeros. At most, I have 3. So when you draw this in, because I know this looks like a random scattering of points, you draw a smooth curve through your points in order. So I'm starting at the top. My graph is coming down to go through negative 4, 5. To get to my next point, I still have to keep going down. Then to get to the next one, I have to change direction, start going up, keep going up, keep going up. Now I have to change direction again to go through 1, 0, and my graph is ending down. And I have my graph. Just make sure you include arrows at the ends for it continuing. And notice it's a smooth curve. I don't have jagged points. Okay, any questions on that? You'll have a chance in a moment to graph one yourself. And when I check the zeros, I do have an odd number, and there are 3. So I don't have more than 3, but I do have an odd number, so that these kind of points check off. I know my graph makes sense based on the degree. Okay, that is how you graph. Then, in example 2, we're actually using this same graph, but what we need to talk about leading up to then is something that is not new. This idea is not new. This is locating the zeros of the graph, so saying what they are or where they're located. So it says if the value of f of x, which is your y, changes sign, so from positive to negative or negative to positive, from one value of x to the next, then there's a 0 between the two x values. We talked about this already with quadratics. This is called the location principle. So it explains it in this box. Suppose y equals f of x represents a polynomial function, and a and b are 2 real numbers such that f of a is less than 0. So what that means, if you look at this graph, at the x value a, that y value is negative. It's below the x-axis. And then f of b is greater than 0. So at b, that y value is positive. So if from a to b, the y value changed from negative to positive, it had to cross through the x-axis in between there. It had to equal 0 in between a and b. So you would say that there would be a 0 when x is somewhere between a and b. Okay, like I said, we did this already with quadratics. So example 2 says determine consecutive integer values of x between which each real zero of the function f of x, same function from example 1, is located. So I'm going to look back up at that graph. I have 3 zeros. And since I have the graph, I can look at the graph to help me find them. I can also look at the table. So on my graph, it looks like there's a 0 between the x value -4 and -3. If I look at my table, when x changes from -4 to -3, the y value changes from positive to negative, meaning there is a 0 between those two x values. Okay, so when I'm listing in example 2 the zeros of that function, there is a 0 when x is between -4 and -3. Okay, there's another one, the second one, looks like it's between -2 and -1 if I look at the table. When x is between -2 and -1, y changes from negative to positive. So there must be a 0 somewhere in between there. So there's another 0 between -2 and -1. And notice these x values like -4, -3, -2, -1, those are consecutive, one right after the other. The third 0 is actually at the x value 1. If you look at your table, when x is 1, the y value is 0. So don't say it's between 0 and 2. The 0 is actually when x equals 1. So if your 0 is between two numbers, you write it as an inequality. If there's an x value where you actually get 0 as a y value, you write it as x equals whatever number that is. Okay, questions on those? Kind of a review from last chapter as well. All right, so then the next part, finding relative maxima and minima. And I'm going to have you actually graph for example 3, but just to talk about what this is on a graph. So this here shows a general third-degree polynomial function. And what it's referencing over here, so point A on this graph is called a relative maximum. And this is since no other nearby points have a greater y coordinate. So a relative maximum, to locate this on a graph, it's kind of like a hill on the graph. So notice the graph leading up to A is increasing, and from A it's decreasing. And then likewise, point B is a relative minimum. And this is since no other nearby points have a lesser y coordinate. This you can locate as a valley on the graph. And notice the graph as it approaches B is decreasing, from B it's increasing. Max and min values are also called the extrema. So if you see that term, find the extrema of the graph. It wants you to find the relative minima, the relative maxima. But then they are also referred to as turning points. So I'm going to go back to my idea of how many directions a function has. So if this is a third-degree polynomial, there are 3 directions. So notice on this graph, it's going down and then up and then down. So 3 directions, down, up, down. There are then 2 turning points. If it had 3 directions, it changed direction twice. So that's what's explained here, the graph of a polynomial function of degree n. So if the degree is 3, it will have at most n minus 1, in which case a degree of 3 would have 3 minus 1 or 2 turning points. So again, just another thing to understand from a graph. Okay, so what I would like you to do, in example 3, you're graphing this polynomial function, and then it says estimate the x-coordinates at which the relative maxima and minima occur. So we are going to go through that part together. I want you to actually graph the function though. So go ahead, practice graphing a polynomial function like you graphed example 1. You can try to answer the x-coordinates where the relative maxima and occur, but like I said, we'll discuss that part together. Yeah, that's the right graph. All right. Those of you packing up, if you did not find the relative max and min, you did not finish the example. Okay, so here's what the graph should look like. For the relative maxima and relative minima. So again, the direction said to estimate the x-coordinates where they occur. You're not estimating the y-coordinate because you don't know that exactly, but you can say near this x value there is a relative maxima, relative minima. So the relative maxima is going to be the hill on the graph. So near this point here, you don't want to list the 5, that's the y value. It's near the x value 0. So relative maxima near x equals 0. And then relative minimum is where this valley occurs. So near that point, the x value is 2. So relative minima near x equals 2. So that would be, you saw an example before, how to estimate the zeros. Here's how you estimate the relative max and min values. Okay, the gold sheet you also picked up on your way in is the graph paper for the assignment. Just note that practice is there. Let me know tomorrow if you have questions.